Now, I would like to talk about the last part of topic 4 of chapter 2 in the book on context-free languages is on deterministic context-free languages. This might be the trickiest and hardest part of this whole course in some ways. What is so interesting about push-down automata and context-free grammars is that if you add, probably the automatons, because the notion of determinism for the grammar don't make sense. If you had a condition of determinism to PDA, you actually create a whole new class of languages that is not regular languages and not context-free languages. They are part of the context-free languages, but they are what we call deterministic context-free languages. And they don't equate, they are not equivalent to context-free languages. They are a subset of them. But they are just a very interesting subset that can be only found and generated through the notion, the concept of deterministic PDA, push-down automata. Okay, so what is a deterministic PDA? Well, it's obviously push-down automata to which we add the condition of determinism. So far, all the push-down automatas we've seen in our examples are non-deterministic. At least we don't impose them to be deterministic. What does it mean to have a regular PDA? Okay, a regular PDA is going to be, you can have a state here 0 and with one same input and one same situation in the stack, you can go to two different places, right? There's no problem for PDA to be defined like this, right? And you can imagine other things, okay? This is not a problem, this is just non-deterministic, and it makes things much easier when you don't impose any determinism here. What deterministic PDA is going to impose is that for one state you can have only one combination of input and stack popping, okay? You can have, something else here, that's okay. That will still be deterministic here, because you will not be in a situation where both of these are possible, okay? Actually, that is not true, and let me explain why. Because when the stack has 1 in there, you can actually either take 1 or take the empty string. So that's a very bad example, but that's very good because I needed to go through the empty string, which is always tricky. So this is okay, okay? This is deterministic, because if you read the input A, you cannot have both 1 and 0 on the top of stack. So you would take only one of these, okay? Same thing if you take the same here, you take the same thing from the stack. Sorry. If you take the same thing from the stack from Q1, but you have different inputs, you are also fine. You're also in a state of determinism. Okay, you do not have two options. You have only one option here and here, because at least one is different, right? For the empty string, we have to allow the empty string for the deterministic PDA. You can look at the definition on page 130. What they say is that the transition function for the empty string must satisfy the following condition. for the transfer function delta, you must be in a situation where either you have the information on the input and what is popped out of the stack, or you have an empty string, but then you don't have any of these. Okay, so you have to only one of the following. Let's be a bit formal here. Only one of the following can exist as an arrow if you want. You cannot have, you have to pick, okay? It's gonna be one of these for each Q, okay? Now, and each A. So the formal definition is, it's one of these cases. If you look at the formal definition by 130, it takes a little while to understand what it actually means. Now, what is really, what it actually is much easier than what it looks. What you really want is a situation where you are never, you want a PDA where you're never in a situation where you can go two directions from one state, okay? You only want to have something deterministic. If you are at a certain state, Q1, and you have a certain set of the stack, you know which way you go without any ambiguity, right? You cannot take two different transition functions, okay? So that's the idea of the deterministic PDA. So we impose a condition on a regular PDA such that at every state of the automaton, you are determined to take only one next state, okay? So you could think, well, it's fairly close to a DFA, but it's actually much more powerful than the DFA because, of course, a DPDA is not a DFA because a DPDA has a stack, right? So it has the capacity to record, write in memory some information. And this leads to a very interesting class of languages. Now, the question that is asked in the books is where they look at the properties of the deterministic context-free languages, right? So we have the same diagram, right? A DPDA recognize the deterministic context-free languages, right? And a deterministic context-free grammar generates. Okay. Now, of course, people who study this field, they thought, well, we know fairly intuitively and even formally it's easy to pinpoint what this is, right? This is easy, okay? We just described it informally, but the formal definition is fairly easy also, and it kind of makes sense, right? You have a PDA and you just make it deterministic. It's an easy notion. Now, the interesting question that follows is, well, there must be a class of context-free grammars that also is deterministic and is equivalent to the PDA. Actually, this is true, except that you need a context-free grammar that has an end mark, an end mark. So we call it an end mark language. So if you add an end mark to your language, it is true, right? So it's not completely equivalent. It's equivalent to an end mark language, okay? What is an end mark language? It's any grammar such that sorry, let's put it that way. Any grammar that is such that it ends with the end mark. Okay, so you know, let's say this one is end marked because whatever language you generate with this AAB, you're always going to end with this little mark. Okay, so it's an indicator that the string is over. It's just a little addition. It doesn't really change anything structurally, but it just makes the equivalent here true. You can actually build a DPDA that corresponds, a deterministic context-free grammar that corresponds to a DPDA if you add this symbol. Okay, it's just a little detail. Now, to show that they are equivalent is a whole other deal, and to explain even what is the very notion of a deterministic context-free grammar is complicated. It's very complicated because it's very hard if I give you a grammar like this one. And T, A, T, B, B, A, B, B. It's very hard to define if this grammar is obviously context-free. That's obvious. But it's very hard to define if it's deterministic or not. And as a matter of fact, it is not deterministic, but showing that it is not is pretty hard. So what is how do we define the determinism when we talk to grammars? And that's kind of the what the author in the book spends so much time trying to define in the section 2.4. I won't go through all the proofs and the details because it would be way overwhelming. But the gist of it is this. Instead of going top down through different steps of derivation as we used to, right? Starting with R, okay. So I'm going to show you an example of derivation, right? That's a derivation, step by step. And this is consequently what we call a reduction. And that's actually an important notion that is used in several areas of theoretical computer science and logic. Notion of reduction. A reduction is really the reverse of a derivation. Okay, you start from a string and you go all the way up to the starting state. So if you have a reduction of a string all the way to the starting state, you can say that this string is accepted. I mean, it's generated by the grammar, right? But you can also think of it, some sense, as the process that a PDA or an automaton goes through, right? It takes a string as an input and it returns an accept state. The accept state being, for us, the starting rule, right? The starting variable. Okay, so that's, you can see already here kind of something that could look like an automaton, right? Of course, it's not going to be that easy because we need something that works for any string, okay? Not just AA, BB, okay? Any string of the language needs to be recognized by a PDA that happens to be deterministic, and that's how we can show that a grammar is also deterministic. Okay, but now let's dive a little bit more into the notion of what does it mean for a grammar to be deterministic. If we accept a bunch of conditions on the way we process the way the rules are built and the way we process the string here, the leftmost condition, which requires that we always go from the left and we start always substituting, reducing here in this case from the left, then we can start having an idea of how it works. You really need to think of a deterministic grammar as some kind of parsing. You have a string, and we are going to parse that string, and that's kind of what the notion of dotted rule that is in the book refers to. You have a dot that is going to move to parse through, okay, here, then here, then here, then here, etc. To parse through the string and try to find what we call a handle. That means there is a chain of a string that surrounds the dot such that we can have reduction here. So for instance, my first handle here is going to be here, right? Until I reach that point in this string, there is no reduction possible given these rules, right? There is no reduction here that happens with A, right? I need to arrive at AB, and AB is a handle for the rule SAB, right? So now I reach that point, I can do the substitution here, and that works. Now that's not that simple because I don't always have only terminals here. I can have also variables, okay? But now I have a variable too, and when I do my substitution, I put my parsing cursor back to 0, okay? I've done my substitution, put it back to 0, and I'm going to move it again, right? Dot A, no handle. AA, no handle. AAS, oh, yes, possibly this, right? Or this. And then I can move it one further here. ASB, because I always read one later. ASB, oh yeah, that's a handle. Now I can do I have a handle here. I can do the substitution to S, okay? So I can replace ASB and I have S now. And I put back my cursor back at the beginning. Okay, so that's kind of the idea. So the notion of parsing is crucial. How do we add the notion of determinism? Well, we need to make sure that when we parse, there is always one way of doing the substitution, not two. And that's kind of the key of determinism for context-free grammars. And that's how you can show the equivalence with the deterministic PDAs. There is a way to determine, and that's called the DK test in the book. So you can look at it if you want to know more about it. There is a test that is such that that shows that for this parsing method, at any point when you parse for finding handles, that means reducible pieces of string around the dots, given a grammar, that for any possible handle, you will have only one possible reduction, right? For any parsing, you will only reach one option of rule. You will never reach a point where the dot is placed in such a way that you could have two options. Oh, I don't know if I should replace S here or here. And actually that might be why this one is not. Now, it's not as obvious as that because you need to take everything into consideration and the parsing mechanism. But if you reach a point where there is ambiguity, basically non-determinism on what is the next reduction, right? So if somehow at some point you have here a crossing road, that's really what it is about, a crossing road. Well, in some sense, if you have a crossing road, you have two possible handles here, you know, handle 1 and handle 2. That is non-deterministic. And therefore, your grammar is non-deterministic. It's not a deterministic context-free grammar. If you guys have one possible handle, which is called a forced handle, all the way, you have a deterministic grammar. And there is a test that allows you to check that the parsing will always lead to a forced handle in any case of valid string. We call a valid string any string that can be on the way from a string in the language on the way of reduction all the way to R. Okay, something that can be in a path of reduction. Okay, so I know it's confused. It's a lot of things. It's kind of very abstract, all of this. But one very interesting takeaway from that is that with push-down automaton, right, we have, again, right, remember we have the regular language, the context-free language. And to which each level corresponds a certain type of automatons, right? We have the finite automaton, we have the PDA, push-down automaton, and later we see the Turing machine. And the recursive languages and all of that. We reached here a very interesting category of languages, the context-free languages and the PDA. Why? Because remember, with a finite automaton, if I make this a DFA or an NFA, right, deterministic or non-deterministic, it doesn't change anything to the languages recognized. Making a finite automaton deterministic is actually, it doesn't change anything to the power of the language. If you take a regular PDA and you force determinism, you create a subclass, right, of DCFL, right? Here. Sorry, it's not very clear. DCFL. A subclass of languages. And that's very interesting because that's very typical of PDA. If you have, that's very typical of this kind of intermediary level, because we'll see that a Turing machine doesn't care if it's deterministic or non-deterministic. I mean, it cares for complexity purposes, but in terms of computing power, it doesn't change anything. So if you're here, it doesn't change anything. If you're here, it doesn't change anything. There is this intermediary level where a PDA is powerful enough to make non-determinism important, but not powerful enough to make it unimportant. So it's kind of this intermediate situation where determinism is going to change everything. I mean, not everything, but it's going to change substantially the category you're referring to. So I think that's a good takeaway here, is that we are in this kind of in-between machine that has sufficient power such that non-determinism is important, but not enough power to make it unimportant again. I mean, unimportant or not as relevant for the category of languages it recognizes. So in this respect, PDAs are a very, very interesting category of automaton. Okay, I hope that cleared up a little bit of this last chapter in the book. It's 2.4, and I'd be happy to welcome your questions. Thank you.